thankful. For very nice performance. Actually, they were going to do it yesterday, but because of the bad weather conditions, they stuck in the mountains. They couldn't reach here on time for the opening ceremony. Today we have here with us Dr. Marty Simon from New York University. Let me tell you a few words about him. He got his PhD in 1986 from University of Massachusetts, US. After a couple of years of work over there, he moved to Pennsylvania State University, where I got to know him. He was my advisee when I was doing my PhD, actually. He stayed there for about 18 years. He stayed there for about 18 years and then moved to New York University. He's a well-known figure about working on how students develop conceptual ideas through a series of well-designed tasks. And he's very delicate in his work, and he has several publications in well-known journals like JRME. He has hypothetical learning trajectories, activity effect relationships. He's written about that stuff. And it's an honor for me to leave the stand to Marty to give his speech.
So I think the microphone is coming back. I invite people who are over here to move, because I'm going to stand here and probably block your view. And also, I can't do this the whole time. While we're waiting, I can do a few more. It's a part of the better. See, I learned something. Günaydın, merhaba. You've now heard all my Turkish. So, I'm going to talk today in the context of mathematics education, because that's what I know something about. If during the discussion you'd like to make a comment or a connection between science education or technology education, that would be fine. There will be time for questions at the end, and you're free to ask questions in Turkish, but only if you want no answer. Okay. I usually speak slowly, but if it's still too quick for you, go like this and I'll slow down further. So this is probably a better title for my talk. I'm going to be describing work that is part of a program of research that we call Learning Through Activity. And the program actually started in the context of some other projects close to 25 years ago, when I was 10 years old. And the first funded project that specifically focused on learning through activity was about 11 years ago. A lot of people have worked with me on this project. These are the people I can remember. And the people in green are residents of this country. Two of them, Gulseren and Ismail, are here today. So for quite some time now, there's been a very strong consensus in mathematics education that conceptual understanding is one of the key objectives of teaching math, and that a rote knowledge of mathematics is not very useful to the learner. At the same time, we have a whole lot of evidence of students not understanding important concepts in mathematics. So clearly we have serious work to do. And that leads to the questions that we try to deal with in the Learning Through Activity program. Questions that we hope to contribute to, but obviously they're a lot bigger than what we can handle. The first is, what do we mean by conceptual understanding? All too often, this term is not problematized, and we go around acting like we agree on it. But in fact, we may have very different ideas or very unformed ideas about what conceptual understanding is. And then how do students develop understanding of mathematical concepts? The basic idea behind our project is that if we understand better how students develop conceptual understandings, we can do a better job teaching conceptual understandings, or teaching for conceptual understandings. And finally, how do we foster learning of mathematical concepts? So those are the questions behind our project, and everything I will say today will be related to these questions. So this is basically what I was saying, that the understanding how students develop conceptual ideas is the basis for instruction if we're going to be successful in promoting conceptual ideas. And Dewey understood this a long time ago. He wrote, with respect to teaching, there is no more important topic than the question of the way in which genuine concepts are formed. So, a lot of people have studied learning in mathematics. And the reason I use the air quotes is because what studying learning often means, and we're talking about some very important groundbreaking work, is it often means identifying steps through which learners pass as they develop a concept. So there's this idea, and then this idea, and then this idea. Sometimes that's talked about in terms of schemes. Sometimes for a more social perspective, it's talked about in terms of mathematical practices. But it's this basic idea of knowing some of the steps that students pass through. When we in our LTA program talk about studying learning, we mean something different. We mean looking at the transitions from one step to the next. If a student is at one step, how do they progress to the next? And we believe that this is really the key to instruction in a lot of ways, in the sense that if we understand how they make that transition, we would be better able to foster that transition. Rena Herskovits wrote about this a number of years ago. She said, in spite of the animated theoretical debate that has taken place on the nature of abstraction, that is the formation of concepts, little experimental research is available, which surmised that the lack of experimental evidence is due to the difficulty of observing the process of abstraction as opposed to the products for which there is more evidence. The products being the steps, the process being how do you get from one step to the next. So, let me tell you a little about what I'm going to try to do in this talk. So in the United States, Christians who celebrate Christmas believe in this, or at least they lead their children to believe in Santa Claus. Santa Claus is the person who brings the presents when the children are asleep. But nobody ever sees Santa Claus. They only see the results of Santa Claus's visit. So the children get up in the morning and there are presents, and that's evidence that Santa Claus has visited. Okay? Reflective abstraction, or the process, the transition process from one step to the next, is like Santa Claus. We say there must have been a reflective abstraction because, look, there's a change. But nobody gets to see Santa Claus. Nobody gets to see reflective abstraction. So in our project, we've tried to focus in and see if we can make reflective abstraction a little more visible. And that's not easy. That's why it hasn't been done a lot. Okay? But I hope you'll get a feel today from the examples which I show you that we're starting to be able to have a feel for that process. So I'm going to provide images of reflective abstraction, and at the same time you'll see some ideas about how we promote those abstractions. Before I do that, I'm going to begin with the first question I showed you, which is, what is conceptual understanding? How's the speed? Am I talking slowly enough?
Yeah.
So, when we try to understand conceptual understanding, what a concept is and how it's developed are intertwined. That is, it's probably obvious that how a concept is developed seems to be dependent on what it is. But it's also true that one of the ways to sort of get a handle on conceptual understanding is to think about what kind of process develops it. What is it the result of? So in 2006, I started from that perspective, and I described a contrast between reflective abstraction and what I called an empirical learning process. Reflective abstraction is stolen directly from Piaget. An empirical learning process is a bit of a modification. I won't go into the details on what Piaget called an empirical abstraction. It's just a little bit broader. So in that paper, I made it clear that mathematical concepts are never the result of an empirical learning process. Now this is different. How many science educators are here? Okay, this is different than a lot of science concepts, right? Because a lot of science concepts derive from empirical results. Okay, math never derives from math concept doesn't derive from empirical result. An empirical result might suggest there's something to look into, but the concept itself is derived in other ways. So let's say that we want our students to understand something about the fact that an odd number times an odd number is an odd number. Okay? So one of the things they could do is they could take their calculator and try a bunch of products of two odd numbers. Right? 5 times 5, 19 times 21, 39 times 37. And they could say, look, they all seem to be odd. What they're learning is that it seems to be true. They're learning that it's true. What they are not learning is the logical necessity of that. This is also a term that Piaget used. Logical necessity means, given the way we think about numbers, there's a reason that an odd number times an odd number needs to be odd. I'm going to go back to this example when I give my examples of reflective abstraction, show you an alternative. But the important thing here is this this empirical work where you put in your two numbers and you get out a product, or you put in anything and get out something else, is not what develops a mathematical concept. It only develops the notion that there's some kind of pattern, but not why that pattern should exist. So mathematical understanding is never the result of empirical learning process. So now let's talk about what actually, when we talk about a concept, what does it represent? And as of a week ago, this is my best statement. In fact, it was in preparing this talk that I formulated the latest version of this. So I'm trying it out on you. A mathematical concept is an articulation by the educators, by the researcher or teacher or curriculum developer, of a goal for students' knowledge of the logical necessity of a particular mathematical phenomenon. That's a lot of words, so I'll give you a minute to reread that. So that's the knowledge that a reflective abstraction is meant to produce. I thought I had it. Yes, okay. So there's something on the next slide, but I want to tell you it first. The two things to remember here are that a mathematical concept is something that the researcher creates. Okay? It's a way of the researcher organizing his or her knowledge about what the students should learn. Okay? It's not what's in the student's head. We can't know that. But it's the researcher's idea about the student's knowledge. Okay? So it's a researcher's idea, but it's about the student's knowledge. So it has to be in reference to the students and what they know. So here's an example of an articulation of a mathematical concept related to an odd times an odd. So I wrote the product of two odd numbers. So this is the logical necessity. See if you can see the logical necessity in this statement. The product of two odd numbers is odd, excuse me, because it represents an odd number of groups with an odd number in each group. Each odd group has one unpaired object. If we pair up all the objects, we get one unpaired object. Each odd group has one unpaired object. If there is an odd number of groups, then there are an odd number of unpaired objects, which means one object cannot be paired. Okay? That's just an example of a statement that could represent the logical necessity that we want students to develop from our lessons on odd times and odd. In a minute, I'm going to show you an example where that goal is what the lesson is designed to develop. Okay, and here we are. All right, so that was the goal. And here's what this lesson is going to look like. We're going to define odd and even this way. We're going to say that even are where we can take all our objects and put them into pairs. So imagine a student working with little cubes. And they can determine whether it's an even number by trying to pair them all. And if they all have pairs, they all have somebody to dance with, then it's an even number. And if one cube is left all alone, then it's an odd number. Okay, and then we have an instructional sequence, and I'm just giving you the highlights of it, where the students start taking a number. In this case, the number is 15, And they have 3 times 15, 3 groups of 15. So I'm sorry, 3 groups of 5. I'm really confused here. 3 groups of 5. See, I spoiled the punchline. The answer is 15. So they pair up the first 5, and there's one that has nobody to dance with, and the second one, and so forth. Okay? So then, in order to determine whether 3 times 15 is odd or even, they have to pair up the ones that had nobody to dance with. So they take these 3, and they pair those up. And they find out that it's an odd number. Okay? Okay, so they do a bunch of problems like this with their cubes, to the point where they get very comfortable with it. They know exactly what's going on. They don't have to think much about it. And then we ask them to do a mental run. And by mental run, we mean, what would happen with the cubes if you did it with the cubes, but don't touch your cubes? Okay? So now if they were doing it, they would say, well, if I had 3 groups of 5, I would put them into the groups of 5, and then I'd pair them up. And 5 is odd, so it would have 1 that would have no partner. And then because there are 3 groups, there would be 3 that have no partner. And 3 is odd, so 3 times 5 must be odd. You see how the abstraction is forming already? Okay? When they have to do these mental runs, they're starting now to anticipate. They now don't need to see the results. I have 5, and if I have 5 and 5 and 5 on the table, I don't have to think about anything. I just pair this. I'm not thinking about anything. Pair this, I pair this. Now I look and see how many I have. I didn't need to anticipate anything. I can just go through it, and the cubes will show me what I need to see for the next step. When I do the mental run, now I have to start anticipating things. Like, if I have 5, will I have an extra one? Okay? If I have 3 groups, how many extra ones will I have? Will that be odd? Okay? So in each case, I'm now connecting my knowledge as opposed to reading it off the cubes. And finally, we get to a stage where they can talk about the general case, which is, okay, if I had an odd number of odd groups, what's going to happen? Okay, so what we begin to see here, and I'm going to show you some more examples, what we begin to see here is how the student's activity forms the basis of their developing the abstraction. And this is in contrast to sometimes people use cubes and then they teach them an algorithm and they're supposed to see a connection between the algorithm and the cubes. This is very different than this. This is their own work with the cubes, their own activity beginning to form that abstraction to the point where they know. We don't have to then tell them what the generalization is because they've already figured that out. Okay, the second example here was from our most recent project. We have a almost 11-year-old, 10-and-a-half-year-old girl who's working on learning fractions with us. And she's faced with the issue of taking a unit fraction of a unit fraction. Her name is Kylie. We call her Kylie anyway. And she's using Java bars, which is a computer program, which you'll see in a minute. So this is Java bars. And the thing you need to know about Java bars is you can make a bar of any size. And our focus is on the length of the bar when we're doing these teaching experiments. And you can partition the bar into any number of equal parts. You can pull out a part, and you can iterate one part or the whole bar as many times as you want. So this is actually, I put all on the same slide, each step, but she goes through one step at a time. So she's given the problem, you have 1/3 of a unit, make a bar that is 1/6 of a unit. Okay? Now understand, she doesn't know how to do that. But she has some knowledge that she can use. In other words, what she doesn't know how to do is how to cut up 1/3 to make 1/6. No idea. But she has some knowledge she can use. So she says, I can iterate the 1/3 to make one whole unit. And I know I can make any fraction given a whole unit. So she iterates, she clicks on the third and iterates it 3 times and makes a bar, and she says, this is 1 unit. All right? And then she says, okay, I need to cut that up into 6 parts. And she starts cutting each third in half, and pulls one of these out and says, that's 1/6. Okay, so that's her activity. And she does several of these tasks. The second task she does is, this is 1/5 of a unit, make 1/10 of a unit. And she does it the same way. She iterates to make the whole unit, and then she subdivides to make the part she needs. Finally, we give her, this is 1/3 of a unit, make 1/9 of a unit. And Kylie cuts the third directly. She doesn't iterate anymore. She cuts the third into 3 pieces, pulls one out, says, that's 1/9. And I said, how do you know? This is a little difficult to interpret, but I will help you. It's unfortunate that the 3 was both the number of thirds and the number of partitions of the third. She says, how many times does 3 go into 9? In other words, she's trying to think about, if I have 3 groups, how many times does that go into 9? In other words, let me figure out how many each group has to have. 3 times, and it's 1/3. So 3 times 3 is 9. And if you cut it up into thirds again, and you take 1, it would be 1/3 of the piece. But this is really 1/9 of the unit. Okay? And then from then on, she's got it. She can do these problems. She can do them with large numbers. Give her a calculator if necessary. But she's got the idea now. She now has conceptualized what some have called recursive partitioning, taking a unit fraction of a unit fraction. Okay? Once again, I think you can see how this particular activity she was engaged in response to these tasks led her to the abstraction that we were looking for. Okay, the third and last example I'm going to give you is Kylie learning to develop the notion of a fraction of a whole number. So once again, she doesn't know how to do it at the beginning. So if you give her a task like 3/5 of 10, she gives you a wrong answer. She might say 2. She might do some kind of other computation with 2 of the 3 numbers in the problem that doesn't make much sense because she really doesn't know how to do it. So we give her this preliminary task, which is, here's a bar, it's 10 units long, show me 3/5 of the bar, and how many units long is 3/5 of the bar? Now, let's see if I can do this. I'm going to try to do it in real time. Where's my program? Oh, I know where it is. Okay, so this is fraction bars. This is our latest version of Java bars. Was developed at the University of Georgia, and then the University of Massachusetts at Dartmouth developed a little more user-friendly version. So I'll show you how it goes. So you click on bar, you make a bar, and she says that bar is 10 units long. Okay, now I need to take 3/5 of it. So I'm going to cut it up into 5 parts. Isn't this wonderful? And I'm going to pull out one of those parts. And then I'm going to iterate that part 3 times. And so that's 3/5 of the unit. And then she says it's 6 units long. Let's go back to PowerPoint. So, and she's able to explain it. She says, well, if the whole thing is 10, then each 5th is 2 units long, and so 3/5 is 6 units long. Okay? She does a few of these problems, and she does a few of these problems. She does them initially the same way, and then very quickly she gets to the point where we'll say, what's 5/4 of 12? I can't remember whether I have a slide for that. Yes. What's 5/4 of 12? And she says 15. How do you know that? Because a 1/4 would be 3, and so they're 5. Right, so it's 15. So once again, we see her making this abstraction. So hopefully you're beginning to see Santa. Okay? You're beginning to have a feel for what does it mean to make an abstraction in a way that you don't get if you sort of give somebody a problem and they can't do it and they can't do it and then they figure out how to do it. And you kind of don't know what happened in between, right? What we're doing is trying to develop the task in a sequence that allows their activity to lead to the abstraction. So 1, it gives us a view of their process, and 2, the task sequence in itself becomes a sort of pseudo-model of what we expect that process to be like, and then when we try it with a student, we get to see whether it in fact unfolds that way. Often we try our set task sequence and it doesn't work at all. And then we have to go back and say, can we modify this? Or do we have to do it in an entirely different direction? Because it's not trivial to try to figure out what are the activities and what are the tasks within that foster that activity that will lead to the abstraction. So I hope you're also getting a sense that it's difficult, but it is possible to begin to study the learning process and not just the products. And that's what I'm going to talk about now. And this is what I was alluding to. Problem solving in math is very important. It's an essential part of mathematics. But when we do problem solving, very often there are some students who can do it and some students who can't. And the students who can do it have a different kind of experience in the classroom in terms of how they can participate in the conversation from the students who can't. And what we're looking for is a way to engineer task sequences that help the student who is not able to make that leap build up to the abstraction that we're looking for, which gives students who are not as well prepared an opportunity to reinvent the idea as well. So this is what our our task design process basically is like. The first two steps are very similar to other processes. We assess the student understanding and we determine an instructional goal. Now the instructional goal tends to be different because it tends to be like the one I showed you, where we're articulating the logical necessity that we're aiming for. Then the real difference in what we do is then we have to identify an activity that the students currently have available. Okay? This is not about teaching them to do something that they've never done before. It's about figuring out what is it they can do. In each of the examples I gave you, the student was able to do each step. They never ran into a point and said, I don't know what to do. Okay? So they were starting with something they could do, and task design was to bring them to an abstraction from the activity they could already do. And then we design a task sequence related to the idea we have about how this learning process can unfold. Okay? And it has to do two things. It has to, I think it says that somewhere. No, not yet. It has to do two things. It has to provoke the students to use the activity. The activity we've identified as potentially useful. And two, it's got to bring them to a point of reflection so that they are developing that abstraction. Right? Because if we just leave them at the baseline activity, they may or may not come up with the abstraction. So for example, if all we did was had them work with the cubes, with the odd number times the odd, that some of the students would have figured it out, but many would not have. But when we do a series of those tasks, and then we progress to the mental run, and then we work finally to the general case, we pick up a lot more of the students. So I hope you see the ways that we're trying to chip away at these three big questions. What I didn't talk today about is how we're thinking about the mechanism of reflective abstraction. If that's a burning interest of yours, you can bring it up in the discussion. So I will stop there. And questions, preferably in English. And I guess if somebody really is more comfortable asking a question in Turkish, then Ismail could translate for me. Yes?
Yes. Thank you. It's very interesting. I just want to ask you one question. I think LTA is related very much to what Figurati said about ZP, zone of proximal development. And then, but we, as a teacher, we need to understand how to scaffold, to make a scaffolding to the student. What do you think about that? Thank you.
Okay. So the question is about Vygotsky's zone of proximal development. The sociocultural theorists that are essentially descendants of Vygotsky have contributed an enormous amount to our understanding about the social historical nature of the knowledge that we develop and the social mediation that goes on. The work that Vygotsky did not get to, and that has not been the focus of sociocultural theory, maybe because it's not the right tool to do the job, is what happens within the individual. Vygotsky talked about internalization, right? That first it's at a social plane, it's at an interpersonal plane, and then it's internalized by the individual. But he didn't explain how this internalization happens. So to me, constructivism and sociocultural theory are complementary. Constructivism doesn't tell you anything about the social nature of knowledge. It doesn't do a very good job at talking about the mediation using language or objects and so on. But this kind of work, I think, does a better job of talking about what that internalization process is. So if you think of the teacher as the more knowledgeable other, or the teacher in combination with a curriculum developer and anybody else who's contributing to student learning, then the question is, how do they best do this? Okay? And in most of the sociocultural writings, that process of mediation is less well articulated. Okay? It's what happens when students are aided by the more knowledgeable other, and then they work towards independence. But how does that process happen? And all mediation efforts are not equal, right? We know some people are more effective mediators than others, right? So it's important to understand what that is, and that's what teaching is about. It's figuring out how to be an effective mediator from that perspective. So understanding where the student's at and what that next goal could be is, in a sense, defining that zone of proximal development. That's a little oversimplified, but it's the best I can do right now. Other questions?
As a result of your talking, I understand the first step is in mathematics, real-life problems, after model, picture, and after mathematization, and after abstract meaning. This is reaching the concept. Is that true?
Yes and no. How's that for an answer? It often is that way. And the reason I say that is because the key, first of all, we're talking about activity. We're not talking about just referring to the real world, okay? It's what is the student doing? It doesn't have to be physical activity, it can be mental activity, okay? But there has to be an activity, and it's the activity that leads to the abstraction. Now, I emphasize again, it has to be activity that the student has available. The student can't engage in activity that's not part of their current knowledge. Often, and depending on the level of mathematics, it's even more frequent early on, often something related to the real world allows students to harness some activity they showed up with, some activity that they had before they came to math class. Okay? But it doesn't have to be. Okay, that activity could be finding square roots, and you could build on that activity. The activity could be any activity, be it mathematical in a formal sense, or some more real-world based activity. So yes, the real world is a great source of activities that can lead to mathematical abstractions. But they don't have to be, the activity doesn't have to be real world in nature.
Yes. Mathematics is, my English is not, pronunciation is not good. I think mathematics is region and result relation. And sometimes students creativity, sometimes we not develop student creativity and mental developing, and maybe in the curriculum problems and concept understanding in curriculum somewhere problems also. We understand.
I'm not sure, so let me see if I understand. I think that you're saying that sometimes when students do mathematics, they get a result, but they don't really see the process. Is that what you're saying?
No, he's talking about curricular issues.
What's that?
Curricular issues.
Curricular issues.
Yeah, curriculum would be part of this.
Did you understand the question?
Yeah.
What's the question?
When students are learning and developing certain concepts, where does the curriculum fit in that
It's
process?
what I say. Is that your question? So, is that your question?
I think some problems in curriculum
Curriculum.
and in mathematics goals. We not allow the students creativity.
Creativity.
And all times we say the students, this is
Right.
this is
The right answer.
yes. All times.
So,
and
yeah. So what I'm proposing is not the way to do mathematics teaching. Okay, it's meant to be an additional tool, an additional pedagogical tool, and also it's meant to be a research tool for trying to understand the process of conceptual development better. As I said, doing authentic mathematical problem solving in classrooms is important. We don't want to ever replace that. And that needs to be done at a level where students can really exercise their creativity. What I showed you is not a hugely creative process. Okay? It's trying to evoke particular kinds of responses from the student, but responses where they are actually developing the abstraction. Not responses where we're just leading them through something. So yes, you're absolutely right, but this is not the tool for enhancing creativity particularly. This is an alternative tool and a complementary tool. Good question.
thank you.
What is the distance between the hypothetical learning trajectory and the actual and effective individual learning trajectory of each child? And when you said that we begin to assess the conceptual understanding of children, how do you think we must adjust the design sequence of tasks when we assess this conceptual understanding during their activity, during a continuous assessment? Not just in the beginning, but during their work.
We are a little bit behind the schedule, so I would like to call Dr. Mustafa Pehlivan to give Mari a little gift for him to remember us when he leaves Turkey.
First time. Thank you for your presentation about our Thank you. your certificate.